Hello and welcome back. Now, okay, I know I've been gone for quite a long time, and I said that we will probably do um, operational amplifiers, but with an AC source. The problem is like I did look into it a little bit, and I have a few books with me, but I don't really have any exercises with AC op amplifiers. And the problem is that I'm not sure if it's like the correct answer or not, if I know how to do it or not. I didn't really have any practice with it, so yeah, I decided not to do it. And I don't really mean the normal easy op amplifier, because if it's got only resistors, and even though it's got an AC input, then the output will be the same as a DC amplifier calculation. It'll be exactly the same calculation. The problem is like I want to do the op amplifier, but I wanted to do it with capacitors and inductors together, and then see how the AC affects the output of it. But again, I didn't manage to do it. I think I had an idea how to do it. I think it's like doing normal AC analysis. The problem is I'm not sure if it's the correct way or not. And I don't want to have a video of me doing it and doing it in the wrong way. It's quite a big difference between getting one of the answers wrong by mistaking calculation, and it's a whole different thing to like get it wrong just because I don't understand the concept of it. And after I said, like, after AC sources and op amplifiers, then I was going to go to transistors. So I decided to do transistors as well, and I realized that I didn't know that much about it either. I didn't know how to probably calculate it. I mean, let me get a piece of paper to show you a little bit of it. We're going to talk about this in a bit, but just wait a second. Okay, there you go, some paper. Now, I did transistors while I was in uni, and I think we were supposed to go more in depth about it before the virus hit. The thing is, like, when they taught me transistors, it was the very basic kind. It was more of this type. You have you have the source or the input. You have the two inputs. Then you have the logic gate, and logic gate is connected to the transistor, and this part will be connected to a high voltage, and then this part will be connected to a resistor, let's say, and then to the ground, something similar to this. Okay, now the way they taught us is that the switches literally work, no, the transistors literally work like a switch. It's either open or closed. If this one was a 1, then the switch will be closed, so all the voltage will flow too. But if this was a 0, then the transistor will be open and then no current flows through it. And they told us it's because it needs a minimum of 0.7 volts for it to function, and if it's under it, then it's simply off. Anyway, and that's what they taught us. Now, I'm sure they tried to teach us in more detail and expand on it, showing us how to do the calculations, or how to do problems with it, or how they function in more detail. And maybe they did and I didn't understand at the time, but as I showed you, that was the main way to use transistors, and I didn't really get the time or chance to experiment with it. Okay, just a second. Okay, and even though like I did a bit of research the past days about transistors, and I can say that I can easily calculate it when it's only one transistor, I still have some difficulties or questions about it when it's two transistors or about other aspects. Now, from what I understood, I made some rules. Okay, so it's something very important that you need to remember that I didn't know at the beginning when I started studying, is that current can travel through the, oh yeah, but these are the three pins. This is the base, this is the collector, this is the emitter, and usually all the current output, it's combined into the emitter, and you'll see in a second why. So the first rule is very important, is that the current travels through the base to the emitter. So current can travel in this direction. Oh, sorry, not the way around. In this direction. Okay. Another is that the collector can travel to the emitter, which will be in this direction. However, the base and the collector has no current going through it. So then there is no current flowing in either of those two directions. Okay? So yeah, just remember this. Through base and emitter, there is a current flowing. Through collector and emitter, it's another current flowing. Those are two different currents, but there is no current flowing from base to the collector. Never. Okay? Right. Now, what's the purpose of transistor is to create a gain, but it's a different with a fixed value, so it's got a fixed gain. Now, the gain is very different from op amplifiers, because in op amplifiers the gain was voltage. You start with 1 volts, you got out 5 volts, and it's a lot more easier to understand and apply the formulas to that compared to transistors, because in transistors the gain is increasing the current. So it's not a voltage gain, it's a current gain, and I don't think you can make it lower. I know with op amplifiers you can make an input of 5 volts and get out an output of 3 volts. That's possible with formulas easily. I'm not sure you can actually do that with transistors, because I have never seen a transistor to give you a gain of 0.1 or 0.02 or something like that. So I think it's only used to increase the current. You cannot decrease the current with the transistor. But if you want badly to decrease the current, you don't really necessarily need the transistor to do it. You can just simply do it with a resistor, if that's your purpose for it. But anyway, next on is that the transistor phase will require 0.7 volts. Again, oh no, it's transitions, sorry, phase will require 0.7 volts. Now, what's the transition phase? Well, as I said from the page, is that to use it in switch mode, you need 0.7 volts for it to close and for the collector to flow to the emitter, to the ground. And if it's lower than 0.7, they'll be open, so there will be no current flowing or any voltage or anything. And that's exactly what I mean by the required 0.7 volts. If the supply is less than 0.7 volts, then the transistor simply won't work, it won't activate itself. And that's why transistors are also used in logic circuits very often. You may think, well, why do you use a transistor in logic circuits? Because if you want the signal from the top to the bottom anyway, you can just use the logic gate. And yeah, you can use the logic gate, but you need to think about that logic gates also have a fixed value too. For example, if you input here 5 volts with the logic gate output, logic gates cannot go higher than 5 volts. If they go higher than 5 volts, they just simply explode and burn. Or it cannot really generate a lot of current either, because of the same reason. And here's where the transistor comes in helping, because you have the small current from the logic gate, but then the transistor will make it into a big current by collecting from the its own source, which is, it can be like any voltage, it can be even 9 or 10 or 20 volts if you want, and that amplified current will just go down from the collector to the emitter, you know. And again, transistors are very useful and really easy to play around and to amplify the current once you learn them. The problem is that I didn't really learn them perfectly and you'll see in a second why. But anyway, when it comes to one transistor, I think it's pretty simple. And here is very importantly, it's very important to know circuit analysis, and I mean it for this one. Before, in op amplifiers, you didn't really need to know circuit analysis. You didn't need to know the current or voltage or anything like that. But now it's very, very important to understand that. And that's because if you calculate the wrong current input going through the base, then you'll 100% calculate the wrong output going to the collector. So you need to make very, very sure to know what current goes through the base. If you get the wrong current for the base, then the whole calculation and whole collector output will be the wrong value. Anyway, this is how the transistors look like. This one is the PNP, I think. No, it's the NPN. Yeah, this is the NPN. Negative, positive, negative. And basically the current will flow downwards. However, this one is the PNP. and this one is a bit more different because it requires the base to have 0 volts to activate, and the current will flow in this direction instead of this direction, so the base will have the highest current really. And yeah, it's basically the same way to calculate this one as well. It's just the opposite of the NPN, because instead of requiring a minimum of 0.7 volts for the, and the higher the voltage the better the efficiency is, instead it's the opposite. If it's 0 volts, then you get the highest current going through it. Anyway, and also if you're curious how the transistors looked on the inside, because that's how they looked on the outside, transistors look like this on the inside. You got the resistance here, in the inner resistance. You got the current from the base going through here. You got the current from the collector going through here, and then you got the current from the emitter. Okay. Now, yeah, and this one is for the NPN, and this one is for the PNP. And you can notice that this is one of the very few kind of like components that use their own current source. And the reason why I show you this is because even though I didn't do AC theory, no AC circuits for this one either, like in the proper with capacitors and inductors, you will need to use this format to do so. And what do I mean by that? Well, when in the DC, it's the input is in the base. No, when the input inside the transistor, it's DC. Then you can use this shape, this diagram, and use these rules. The problem is like when it's AC, then you are forced to use this one because the phase will change it, and there are a few more extra rules to follow. But as I said, don't worry about this. We won't do this because I don't know how to do it perfectly either. But eventually when I start my new year, which will be soon in October, we'll go through AC theory in op amplifiers and also in transistors. I'll have a better understanding about them. Okay, so let's get started then. I'll put this page here and we'll go with the first exercise, which is this one here. This will be your typical transistor exercise or your typical transistor circuit. A very simple one. Got 3 resistances at each end, and we get the gain, and you kind of always get the gain in exercises. And I was curious, like, why do you get the gain? How do you know this is the gain? Because the gain is very important. It tells you what the current out of the collector will be and how much bigger it will be from the base. And this is one of the things that I said I don't really know the answer for it, because I was looking at transistors and there are many types of them, and they have different gains. Some of them have actually range gains. They have like between 100 and 700. And even in books that I read about transistors, because I have a couple of them here, they were saying you can't really always trust the reading from the data sheet because they are designed to be inaccurate. They are designed to give you a range. So when you use a transistor, you are not always 100% sure if it's 100 gain or 200 gain or 300 gain even. Yeah, sorry about that, the postman came over, so I had to pause. So anyway, yeah, as I was saying, I'm not 100% sure how the gain works. Some of them said they are about the voltage input or even the current, like the more current or voltage going through the base, it kind of determines between that range of 100 and 700. Now, as I said, like in rule 2, the gain B is calculated as a fixed value. This is what I mean. I mean, like when you do the calculation and you calculate for the transistor, the gain, it always stays the same. But again, I don't really have the equipment to test it here at my home to see if I can actually change that, if I can make the gain to get higher or lower depending on the input. But anyway, we'll solve this problem without worrying about that. So all the problems that we'll do will have a fixed gain. The gain won't really change. Now, how do we solve this? Well, there are a few things that we can do. One of them, we can mark the currents we know this current IB will go in this direction, IE will go in this direction, and then IC will go in this direction. That's one of the things we can do. But another thing we can do, and we always should do, and the reason why I say that circuit analysis is very important, is that we can apply mesh to it. You know, the one that you do the two loops, one loop here and one loop in the same direction here, and then we can call them, let's say this one will be I1 and this one will be I2. And you may say, well, Alex, why do you use this mesh? Because you said there's no current going to the base in the collector, and there's no current going through here, but there is current going to this two. And the way to determine the current IB would be to apply mesh and find the current total. Because remember, this E, the emitter, has a different current from IB. And you can't really do 5 divided by 10k and be like, well, I just do 5 divided by 10k and then I get the current for B. It doesn't work like that, because there is also a current through IE and there is also a resistance here. So you need to include this as well. That's why we have to apply mesh here to calculate it. We can apply mesh, or we can even apply Kelvin's voltage law if you want. You know, we can apply many types. So I think I'm going to go to with Kelvin voltage law because it's simpler in this case. So I mean, I say it's simple, but it's basically the same thing, isn't it? So yeah, let's see here. So KVL, they'll be equal with the voltage 5. Very importantly, it does not stay positive because it starts from this point, and then it goes down because of the 10k, so minus 10k, and it will use the current IB because follow this path, 10k IB. Then next will be E. Now it will go through here, but remember there's a transition point here of 0.7 volts that's required, so that will be also minus 0.7 volts before getting to this resistor here at the emitter, and then minus 200, and then it will be the current IE. And you may see this and you may be like, well, Alex, this didn't really solve the problem because, well, we don't know IB and we don't know IE. We don't know either of these two currents, B or E. So what we do? And here's the thing. I didn't write the entire thing yet here because I wanted to keep it simple for now. I didn't want to make it confusing. There's an important formula saying that the collector IC will be equal with the base, the gain, multiplied by IB. And that's very important. And you may say, yeah, but that's for IC. What is it for IE? Well, IE is simply the sum of the two currents. It's simply IC plus IB. Okay? So these are the two rules. No, it's just kind of like the two formulas that you need to understand, and that helps us solve the problems. And what do you mean by helping us solve the problems? Well, because now we can exchange this IE into IB. And how do we do so? Well, we know that IC is equal with IB times the gain, which our gain is 100. So I will actually write it here. So we know that IE is equal with IC plus IB. And we also know that IC is equal with the gain times IB. So that will be equal with 100 IB because of the gain here. Okay. Alright. Then let's see here. Sorry, my throat hurts a little bit. Okay. So now IE, we can replace it with, instead of IC, we can replace with 100 IB plus IB, and that will be 101 IB. Okay, so now we can see that we can replace IE with this value here, and then we get IB in the equation, and that will make it solvable because we have only one unknown instead of two unknowns. Okay, so KVL, that will be equal to 5 minus 10k IB minus 0.7 minus 200 times 101 IB, or you can just leave it as 2000. Yeah, let's put the times so it's more clear, but clarified between them. Okay, I'll move this a bit. There you go. Now what do we do next? Well, we just simply calculate it. So we can say that inside KVL we can put 0. It's equal with 5 minus 0.7, that's 4.3, minus 10k IB, and 200 times 101, that will be equal with minus 202k, 20.2k IB. Okay, so now we can just calculate it. We can move this on the other side and add those two together as a negative. So that will give us minus 30.2k IB equal with minus 4.3 volts. Okay, and therefore IB will simply be equal with 4.3 divided by 30k.2, and that will be a positive value because both are them negative, so we can just change them in positives. There you go. And that will be 142.38 microamps. And you may say, well, maybe it's something wrong with this, because this seems very, very small. Imagine like using only microamps that cannot power anything. But again, remember, it's got a gain of 100. So the collector will have a different current. Okay, but we are not really interested in the collector current. We are more interested in the voltage here. Okay, but we also need the collector current in a second, and you'll see what I mean by that. So the voltage output, that will be equal with, so the out will be equal with, will simply be the current IE multiplied by 200 ohms really. So it just simply be IE times 200, and then that will be, therefore the out, that will be equal with 142.38 microamps. And remember, IE is like 101 times bigger, so it'll be times 101. Okay, and then we multiply that one by 200 as well. Alright, and when you do this calculation, then the answer that you'll get will simply be 2.876 volts. Okay, and that's the voltage output that we'll get here at V out. And the current, if you're curious, at the emitter E, there will simply be, let's see, 142.38 times 10 to the minus 6 multiplied by 101, that will be 14.38 milliamps. Okay, so you can see that this problem is solved. Another interesting thing is that each section has its own voltage. So BE is voltage, it's 0.7 volts for like most transistors. And again, remember that the 0.7 can be interchanged as well. Like you may have transistors that use 1 volt or sorry, I think the recording cut. So I was saying like some problems ask you to do VCE as well, which is the voltage between point C, the collector, and the emitter. And I was doing here the formula. You can apply Kelvin's current voltage law, and that will be simpler because you already know the current through IC and you also know the current through IE. Now, the way you do it is you use the 12 volts and then you take it away by the 100 ohms, and that will be multiplied by the current IC because IC is going to the 500 ohms, and then you take away again by the 200 ohms, but this time with the current IE because IE is going through it. And remember, you also need to take away the VCE because it's in the way, VCE. And I just wrote the formula down here for it. 12 minus 500 IC minus VCE minus 200 times IE. That would be 12 minus 50k IB minus VCE minus 20.2k IB because I convert them to IB values. this one will be 100 IB, this one will be 101 IB. Then I rewrote it here again, and I was at the last step of writing it VCE equal to 2.005 volts. So that will be the voltage drop inside VCE right here. And let me check something. So we know the voltage drop at the Vout is 2.876. Then theoretically, if I do, let's see here, 142.38 times 10 to the minus 6, we can check this together, and then we multiply by 100, and that will multiply by 500. Then we'll get 7.119 volts drop here. Now if you add this one by the VCE, which is 2.005, and we also added by the voltage drop here, then that one will be 2.876. Then we should get exactly 12 volts, the exact voltage right here. So there you go. This is a way to check to see if you actually did the calculation properly, because in Kirchhoff's voltage law, all the voltages, voltage drops added together, they should give you the same voltage as in here. And the same can be applied here as well with this one. And I guess I can prove it to you as well right now. So 10 times 10 to 3, that one will be multiplied by 142.38 times 10 to the minus 6, and then that will be plus 0.7, the voltage drop here, plus the 200 times 142.38 times 10 to the 6 times 101. And oh, did I do something wrong? So, oh, I forgot to put the minus. There you go, minus. Yeah, and there you go, 4.9999876. So yeah, it's basically 5 volts. And there you go, this is how you also check the problem. And don't worry, this is not the only example. We are going to go through many of them because I have quite a few of them prepared. Anyway, yeah, so in the next example, let's keep going. Now, this problem, you'll notice that's already quite different. Why is that? Well, there is no resistance at the emitter in the first place, but what you notice is that the voltage in is actually a peak voltage, which means it's an AC source of 2 volts, and this new word called saturation of 0.2 volts, and the saturation of 0.2 volts, it's inside VCE, and this saturation just means that the VCE will be a bit lower, let's say. Okay, I mean, it doesn't really make that much of a difference. It only makes a difference when you calculate the voltage going through it, and you'll see in a second what I mean. But the important thing is that with the peak 2 volts and the AC source, the reason why we can do it like this here, and I can't do like different more complex AC circuits or amplifier, is because again, the reason is that it's only resistors, so it doesn't really change anything. You don't really need to change it to the RMS value, and you don't need to worry about the phases because the resistor got a phase of 0 degrees, so it just stays the same. So there will be the same phase on the input as the output. So if you have one of the problems that asks you to calculate the peak value, don't worry too much about it, or don't stress too much about it, because it doesn't need any complex numbers. It just simply needs the same way to calculate it. The only difference is that instead of a straight line coming in and coming out, it's an AC sine wave coming in and coming out. Right. So you can, if you, sorry, it doesn't go. If you like, you can pretend that this is a box, and that it goes in this direction inside the box, and it's at the box for this one that goes in this direction as well. I mean, if you want to, and if don't, you don't need to. Now, another advantage of this circuit, and why it's a lot simpler than the previous one, is because there is no resistance at the emitter, so there is no IE that we need to calculate. So you can simply write it as the peak, which is 2 volts, minus 12k IB, and then minus the 0.7 volts here at the transition. And that's it, because there's no resistance, therefore we don't have voltage at the point IE, because it's also connected to ground. So then therefore there will be minus 12k IB equal with minus 1.3, and we can write it as IB will be equal with 1.3 over 12k, okay, and that will be equal with 108.83 microamps, and that's the current to the base. Now we need to find VCE, and it's got a saturation of 0.2 volts. What does that mean is that on the top of the voltage drop, it also takes an extra 0.2 volts. So the way we calculate is we just simply do 5, the source, minus the transition, which is 0.2, over the resistance, the capacitance, which is 4.8k. And because there is no emitter resistor, we don't really need to worry about the voltage drop here, because the voltage drop here is basically 0, so we just need to worry about the top side. Okay, and then that will be equal with 1 milliamp, and there we have it. Now we can also do another interesting things. For example, there is something like this is the base beta, and it's also an alpha, and the alpha also tells you the gain, but it tells it to a more special way. For example, if somehow you know the value of IC and you also know the value of IE, then you can find the alpha. And usually the alpha, it's something, let me put like 3 dots. Usually alpha, it's less, no sorry, not more, it's less than 0.99 recurring 9. So it is always under 1, because again, the way it works, you simply do the value IB over IE, and I'll show you in a second actually. But anyway, actually I can write it to you here, because we know that IE is equal with IC plus IB. Another way to write this alpha will be to just write it as simply IC over, and then we replace the IE with these two, IC plus IB, okay, and you can apply this formula, and that way you find the alpha, which can be used to determine the other two values, to either determine the beta or to determine the emitter if you want. Okay, well again, you very rarely use alpha, because most of the time you'll know the base current IB, and very rare, and because IB, you'll know the beta as well, the gain beta. That's why I don't really use this one. I use it very rarely, and I'll just show you how to calculate it in case you never ever need to use this. Alright, and the way you do it is quite simple actually, because this value here, as we calculate it, is the value of IC. That's IC, and this one here is the value of IB. Okay, so we can do alpha equal with IC over IC plus IB, and that will be equal with 1 milliamp over 1 milliamp plus 108.33 microamps. Okay, and then that would be equal with 0.902. okay, and yeah, that's basically the way you do it. But now, as I said, finding the beta, it's a lot easier and more useful. So you can also find the gain beta, which this one, instead of being IC over IE, instead it will be IC over IB, and that will be equal with 1 milliamp over 108.33 microamps, and that will be equal with simply 9.231, and we can put bracket gain. There you go, and that will be the current gain from this point here to this point here. Now the trick about this one is that we know the voltage input, which we know for the other ones as well. Yeah, it's kind of curious. I guess the only reason why this works in here but it wouldn't work in like a previous example, like in this one here, is because we don't have any voltage drop going through the emitter. Because if you had voltage drop going to the emitter, then we wouldn't be able to exchange the IE from here to the IB value because we don't know the beta. So yeah, you can find the beta in the alpha, but that's quite hard because it requires you to not have any resistance to the emitter. Anyway, so yeah, that's basically how I calculate it. Thank you for watching this exercise, and we'll go to the next one. Okay, now this exercise is very similar to the previous one, as you see here, but the difference is that we've been given the gain and we are asked to find the V out here. And this one, we've been given the saturation, and I guess we have to find out the gain. At the start I said that we need to find VC, but VCE is very simple to find out because as I did here, it's simply 5 minus 0.2, so that will be 4.8 volts drop in there. So yeah, but anyway, let's get back to the problem that we have to do, which is this one here. Now we can just simply apply the same formulas in practice, really. Just going in this direction here, and the same applies for here. And again, we have the collector, we have the base, and we have the emitter. But the emitter, it's just empty, there's no resistance through there. So again, it's very easy to calculate. Now, we know that from this point to this point, from the base to the emitter, there will be a 0.7 volts drop. Okay, so we can apply Kelvin's current law, Kelvin's voltage law, okay, and then we can do 5 minus 0.7, 5 minus 0.7, and we divide it by the 200k, and that way we find the current IB, which will be 21.5 microamps. IB. Alright, now the reason why this works here like this in such a simple manner again is because there is no resistance to the emitter. If there was resistance to the emitter, then we will have to do a few extra steps like in the first exercise. But anyway, let's keep going. So we know the gain is 100, so and we need to know the IC. So we can simply do IC equal with 100 times IB, and that will be equal with 100 times 21.5 microamps, because again it's 100, and that will be equal with 2.15 milliamps. Quite big, to be honest. Anyway, now what we need to do is to find V out. Alright, so yeah, now let's calculate the V out. And the way we do so is to take the 12 volts minus the voltage drop in this resistor, which will be 1.2k times 100 IB, or we can just do like times IC. There you go, that should make it easier. And then minus another voltage drop, which is V out. Okay, the ones that we need to know. So therefore we can write it as 12 volts minus 1.2k IC equal with V out. There you go. And then therefore this will be 12 minus 1.2k times 2.15 milliamps. That will be equal with V out. Therefore V out will be equal with 3.42 volts. There you go. And that is basically the answer. Now, transistors aren't perfect, and sometimes you get like a 10% increase or 10% decrease, and your teacher might ask you to like calculate the probability as well. So we can also write as therefore V out, like the ideal will be 3.42 volts. That will be ideal. But because of saturation like we saw in the previous exercise, maybe it's like 10% or higher or 10% lower. So V out, if it's 10% lower, then that would be 3.678 volts, and that would be minus 10% IC in the current. V out, if the current is higher by 10%, that would be, wait a second, is it 3 or is it 9? I might have written wrong. That seems too small. 12 minus 1.2 times 3 times 2.15 times 10 to the minus 3. Oh, it is 9.40, sorry. It's not a 3, it's a 9. There you go, 9, 9, and 9. Alright. And then this one here will be 9.162 volts if the IC is plus 10% IC. Well, I already calculated this one like off screen, but I guess I can just show it to you as well. So let's say this one 2.15, the IC will make it 10% lower, so 2.15 divided by 10, that will be 0.125. So we'll do 2.15 minus that answer, and that will give us this current here. Then we can do 12 minus 1.2 times into 3 times the answer. Oh, sorry, I forgot to put the milli. I need to start again. Okay, so 2.15 times into the minus 3 divided by 10. Okay, and then we do 2.15 times into minus 3 minus that answer, and that will give us this number here. And then we do 12 minus 1.2 times into 3 times that previous answer, and there we have it, 9.678. And that's how I did. That's how you calculated if it's 10% higher or 10% lower, because sometimes they can be inaccurate and you can't really always measure them. And what I mean by inaccurate is not like a big difference, like this one being 100 and being inaccurate that would be like 200 or anything like that. No, being inaccurate is more like maybe maybe the gain isn't a perfect 100, maybe it's just like 105 or 110, and you just put the range of like plus minus 10% to like make sure that you cover all of it, that you'll use one of the values between those two values, you know, instead of like relying on the ideal. All right, so I'll put this on there, and I'll see you in the next exercise. Right. So this is another exercise. Now this one looks very familiar to the last one, but you notice something different. You notice that it's an arrow upwards here, and I also notice I wrote bigly here P and P. And yeah, there are more, as I said, there are more types of transistors. It's not only the NPN, it's also the PNP. And let's do some exercises with this type of transistor and other type. And yeah, now don't think that all transistors are just this. There are F-gas transistors as well, which they look very different, and they have drain, something called drain as well. And yeah, there are many types of transistors as well. But as I said, the only ones that I learned are these ones, because these are the ones that I encountered so far. When I learn about other types of transistors, then I'll probably do videos about that different types as well and how to calculate them as well. Alright, now let's get started solving. Let's see. So the action we'll probably want to do, the action doesn't really matter. What it matters is that it's the same for both ways. So let's do it in this way as well. And let me mark with another color. Okay, the way this is supposed to work is that IE, the current, is supposed to go upwards, and it will flow through here, going to the collector as well through IC. Now IB doesn't go in anymore because it activates when it's 0 volts going through here, so it will go outwards instead, and that will be the IB. Okay, right. Now, how do we calculate this? Well, also remember that it's also the 0.7 volts in here as well, and we calculate the exact same way. We start from the emitter, this point, because this is kind of the source, and that will be 10 minus 0.7 minus 500k, and very importantly that's IB, is IB going through it, minus again 2 volts. Okay, so then therefore minus 500k times IB will be equal with, so minus 2 and minus 0.7, that'll be minus 2.7, and that minus 10, that give us 7.3, move to the other side, that'll be minus 7.3 volts. Okay, then IB would be equal with 7.3 over 500k to find IB, and that will simply be equal with an extremely small amount of only 14.6 microamps. There you go. So we can already see how useful the transistors are on detecting very small signals and making them a lot bigger, because this has got a gain of 100. So when you calculate the IC, then that will be equal with 100 multiplied by IB. Therefore, to the IC, that will be 100 times 14.6 microamps, and that's equal with 1.46 milliamps. Okay, and that's the current going through IC. Now, remember that our purpose it was to find VCE or V out, whatever you want to call it. So let's just call it V out. No, let's call it VCE actually. Okay, so then therefore the value of we will loop this way, so that will be 10 no wait, so that will be 10 VCE are going in the same direction, but the 2k it's the opposite direction. Okay, that's it. So that'll be 10 plus VCE minus 2k times IC, and that will be equal to 0. Therefore 10 plus VCE minus 1.46 milliamps multiplied by 2k, that will simply give you 2.92, and that will be equal to 0. Therefore minus VCE will be equal with, we'll move it to this side and move this both to this side, that will be minus 7.08. Okay, therefore VCE will simply be equal with 7.08, right? And then we can do this is one way of calculating, but it's also another way of calculating this is to do, so we know that VCE is made of two voltages, the voltage VC and the voltage VE, so we can also write it as VE minus VC. Alright, and therefore there's 10 volts at this point, so that means VE is equal to 10 volts minus, and then we this 2k ohm resistance, and we know that IC is equal to 1.48, so that'll be minus 2.92, and that will be equal with again 7.08. It's just another way if you want to calculate it in this method here, or if you want to simply calculate it all together in this method here. Depends, maybe you want to like know the specific value, maybe you want to know the specific value of VE or the specific value of VC. So then using this formula here, it's a lot easier to do so. Okay, so yeah, that was it for this exercise here, and let's pause here and we'll go to the next one. Okay, on this one the drawing looks a little bit wrong, but that's because I mistaken when writing the notes inside of it, because I was asking in this question because the resistances, as you know, they usually have a 5% higher value, upper value, or lower value. Okay, and I was thinking, let's calculate the value of VCE with this 5% in mind, and trying to find the maximum voltage I can give out, or the minimum voltage that can come out of it. And that's the reason why this is so. Anyway, but we can apply the same formulas. So there's one loop here and one loop here. It starts with 0 because it's 0 here, so that'll be simply 0 minus 10k times IB minus 0.7 minus 10k times IE. Minus and minus, that'll give us a plus 12 volt. Okay, and all of it will be equal to 0. Now we just need to calculate. So minus 0.7 move to that side and that side, so that will give us minus 11.3 volts. That was simple enough, and that will be equal with minus 10k IB minus 10k times 201 IB, because the gain here is 200, and IE is equal with the gain plus IB. Alright, therefore minus 11.3 volts will be equal with, so let's calculate here, 10 times 3 plus 10 times 10 times 10 to 3 times 201, 2.02 mega. Alright, 2.02 mega ohms. Therefore IB would simply be equal, because it's AB as well, will simply be equal with 11.3 over 2.02 mega, and that's equal with 11.3 over 2.02 times 96, 5.6 micro, 5.6 microamps. Alright, then the next step will be to calculate the VCE. It should be quite simple. We should do it like this. So then that will be minus 12, okay, minus the 10k ohms times IE, oops, alright, minus VCE minus 4.7k times IC minus 12. Alright, so yeah, we can rewrite this one as we change the IE with 201, so 10 times 3 times 201, that's equal to 2.01 mega ohm IB minus VCE minus, and oops, sorry, I mean it meant to be 200, was it? Wait, IE, yeah, and now 200 at 4.7, that's equal with 940 k IB, and that's equal to 24. Alright, now we can replace the values of IB, so that will be 2.01 times 10 to the 6 times IB, which is 5.6 times 10 to the minus 6, okay, minus 940 times 10 to the 3 times 5.6 times 10 to the minus 6, and that's equal with about 5.992 volts. Okay, right, 5.992. That's quite a low voltage. Let me check if it's correct. So that's millivolts, yeah, that's kilo, yeah, that's milli again, and that's mega. Okay, let's use 5.992 then, I guess. Okay, so then therefore 5.992 ohms IB will be equal with 24. Okay, so then therefore IB will simply be equal with 24 divided by 5.992, and that's equal with 24 divided by 5.992. That'll be basically 4 milliamps, no, 4 amps. Okay, so wait, oh no, what have I done? Okay, oh, it's minus VCE. Sorry about that, I lost my concentration. For a second I thought I was calculating IB. Sorry, never mind. That's why I got the wrong answer, because it wasn't the VC and that, and this wasn't supposed to do. Yeah, again now. Okay, so then therefore VCE will be equal with 24 minus 5.992, but this one was supposed to be negative, so it will become a plus, no, there is something wrong in this one. So this one says negative. I gotta take K here, 4.7K here, and the 12 that's negative. Together it'll be minus 24. Move to the other side, it'll be 24. Good. Then why is the VCE such a big value? So IB does the 10K, so that should be fine, and this one should be also fine. Okay, let me calculate again. Let me put them again in the calculator. So 10 to the 3 multiplied by 201. That's the mega value. 4.7K multiplied by the value of IC, so that'll be times 200. 940. Okay, 2.01 times 5.6, 5.6 times 10 to the minus 6. Okay, wait, there you go, there's the multiplication there, minus, let's see, 940 times 10 to the 3 multiplied by 5.6 times 10 to the minus 6. Right, and oops, something is wrong again. So that's mega, that's milli, that's kilo, that's milli again. 5.992. Oh, I think I get it now. Okay, because let's see. Because this one will come out in this direction. No, this one goes in this direction, and this one goes in this direction. Alright, let's calculate it that way. So this one, which I know it's wrong because there's too much, 5.992, this one will be equal with 18.008. Let's do it the other way now. Let's do VC minus VE. So VCE is equal with VC minus VE. And that will be equal with So that will be 4.7 times 10 to the 3 times 200 times 5.6 times 10 to the minus 6. Okay, that will equal with 5.264. Okay, but that's the drop here. So that'll be 12 minus the answer, and that'll be, so at this point here, at point VC, that'll be 6.736. Alright, now let's go to the other one. This has minus 12. So then that'll be 10k, that's in the 3, multiplied by 201 times 5.6 times 10 to the minus 6. Okay, that one will be equal with 11.126. So minus 11.256. The problem is this one here, the 12 volts minus 12 volts, like what do I do with it? And I think it just stays like that. No, it's a minus, then we take it away from this one, so it'll be minus 11.156 minus 12, okay, and that'll give us 0.744, so that'll be minus 0.744. Okay, and then this one will be 6.736 minus 0.744. That will be equal to 5.992. 5.992. But again, like, how do, is this the ideal one? I'm sorry that I'm this confused about it, but honestly I'm not sure why I keep getting this value. Okay, let's say this is the value. If that's the value, then I should get 0 when I do minus 12 minus 10 to the 3 multiplied by 201 times 5.6 to the power of minus 6, right, minus 5.992 minus 4.7 times the 3 multiplied by 200 times, let's see here, 5.6 times 10 minus 6, okay, and then minus 12. No, again, it's the wrong value. I wonder why. So minus 12. Let's get the 12s out. Maybe they just cancel each other. Let's try it that way. No, that's still not correct. So there's a current in milliamps, and there's the resistance here there. That's supposed to be the voltage drop. In that one it's supposed to be 10k. Oh wait, there's a minus there. Oh, there you go, it does give me 0. Okay, so it is correct. Huh. Alright, so I guess that the answer is this one here. So this one here is the ideal. Okay, so this one would be like that center when our components are the ideal components, when there is no 5% increase or decrease inside of it. Alright, now can we make this shorter? I guess we can. Okay, so at maximum we can reapply this formula here, and then right, this formula here, and then therefore there'll be minus 12 minus 10.5k with the 5% increase, i.e. minus VCE minus 4.7, no wait, with the 5% increase that'll be 4.935k, okay, times IC minus 12. Alright, so then therefore VCE would be equal with, so let's do it here, minus 12 minus 10.5 times into 3 times 201. Alright, that's 5.6 times 10 to the minus 6. Okay, then the next one is VCE, so we ignore this one, and then again minus 4.935 times into 3 multiplied by 201 times the 5.6 times 10 to the minus 6. Okay, and then minus 12 again. Alright, oh no, this is supposed to be 200, not 201. There you go. Wait, this one is supposed to be 201, the other one is supposed to be just be 200. It makes a really small difference, but I guess all differences matter. No wait, the other problem is that now this IB is changed as well. So it's not 5.6 anymore. Oh god, no. Meaning that we need to do all the progress again. You know, this already took me almost 20 minutes, and it was just to calculate one of them and to find out which one is the ideal answer. I guess let's do this instead. I guess your homework would be to like solve it when it's a 5% increase and 5% decrease. You basically do the same thing, but instead of having 10k here, you'll have 10.5k for the upper one, and this one will be 9.5k on the lower one. The same for this one, it'll be like 10.5k for the higher one, and then 9.5k for the lower one, and then the same for this one, 4.935k for the higher one, and then the lower one will be, wait a second, 4.7 divided by 10, then we divide by 2, and then we do 4.7 times 3 minus the answer, and that will be 4.465k ohms. Alright, so I guess as homework you need to do this exercise and calculate it with these values, and if you get 0 when calculating this here, that means your calculation is correct. Anyway, so yeah, thanks for watching this exercise. Sorry I didn't finish it, but if I have to like finish it, I'll need to like redo all the steps again with a small change in the resistance. So thanks for watching this one, and I'll see you in the next one. Alright, so let's keep going. Now we're going to do another couple of simple problems. After a couple of simple problems, we are going to go to the more hard stuff. Now, this one is very simple again. The only difference is that now the base is even smaller with 1 mega ohm. And we need to find the voltage in VCE. And also you'll notice that there's 0 volts going through the base through here, and there are 0 volts through here. So it'll be quite interesting when we try to calculate it. Why? Well, because as you know, in rule number 4, in transistors, the transistor phase requires 0.7 volts. Alright? But because it's 0 volts in here, so let me be with that. There are 0 volts in here, and there are 0 volts in here. That means that there is no current flowing through here, meaning there's 0 volts in here as well. And what we have left? Well, let's see here. So if IB is equal to 0 amps, Therefore, IC is equal with 100 multiplied, or 200, whatever this is, 200 multiplied by 0 amps, and that will still give us 0. Alright, and this point here, VC, the VC here, that will be equal to 5 volts. And this point VE here, as I showed you, would be equal to 0 volts. Meaning that therefore, the voltage drop in VCE will be equal with VC minus VE, and that will be equal with 5 minus 0, and that's equal with 5 volts. And there you go. VCE's got a drop of only 5 volts. There is not more than that or less than that, because again there's no current going through here, so that means all the voltages dissipate at this point before reaching VE. Alright, so this is how you solve this one. Very simple. The point of this exercise is that I want to show you that if there is 0 volts going through the base into the transistor, then there will be 0 volts at the emitter point as well, or the emitter point won't change. And then you'll only have the collector voltage going through and no current either going through it. So basically this will be a dead circuit, it just simply won't do anything. Anyway, thanks for watching this one, and we are going to go to the next one. Okay. Now, this one is a bit more strange and a bit more different. And why is that? Well, this is because it's an NPN, but also, not only that's an NPN, it's an upside down NPN. And you need to be careful about this sometimes, because some circuits should display the transistor, but it might throw you off if it's upside down. Instead of the emitter being at the bottom and the capacitor being at the top, is the other way around. Alright, but remember that VBE will still travel this way, so there will still be the 0.7 volts drop in here. Okay, so I'm just saying this so you don't make the mistake. And also for NPN, let's mark the current, so it will go to the emitter like this, and then it will go out the base and also out of the collector. So this one will be IE, this one will be IC, and this one will be IB. Something else strange that you may notice is that we do not have a gain, but also there is no resistance in the base. So how do we solve this? Well, it's quite simple, because we can determine this point here, which will name it VE. So that point there, VE, will be equal with the voltage here, 0.2 volts minus, no, plus the 0.7, plus 0.7, because in an NPN you rather add them together instead of take them away, and that will be equal with 8.9 volts. Okay, very simple so far. Now you need to find the current IE, and now we can use the value here of VE. So we can say that IE will be equal with VE, no, 10 minus VE over 1K, and that's equal to 10 minus 8.9 VV over 1K, and that will be equal to 1.1 milliamps. Alright, and because there's usually such a small difference between the current IE and IC by only 1 IB, which sometimes this can be even microamps, then we can assume that IE is got the same value as IC. So we can assume therefore that IC will be approximately 1.1 milliamps. Remember, this is just an approximation. It's not 100% accurate, because again we don't know the gain, so we can't know the value for the BIB. So this is pure assumption. Now what we do, we can find the value, this VC here. And how do we do so? Well, we simply do VC minus 0 over the, oh no, wait, this one will give us the current, never mind, sorry. Okay, to find VC, we'll multiply this 3.6k ohms by the current. That'll be 3.6k ohms multiplied by the current 1.1 milliamps. Okay, and that will give us 3.96 volts. There you go. And now we can determine the value of VCE by doing VC minus VE, and that will be equal with, we got let's see, so VE that will be 8.9, okay, and VC that will be 3.196, okay, so that will be 3.96 volts minus 8.9 volts. So then the value of VCE will be equal with simply minus 4.94 volts. Anyway, wonder why is this one a negative value? Why is it not positive? Well, because it's supposed to be the other way around. So it's not plus minus VCE in this direction, because that one is minus 4.94 volts. Instead, how it's supposed to be, it's minus plus VCE, because that would be 4.94 volts. Okay, so that was the right, so that was the exercise, and I hope you understood it. And remember, we are able to do so. Why we did here, why we assume that IE is equal to IC, is because we don't have two important things. One of them is being a resistance IB, so there is no way we can find this one, and because we don't have this resistance here, that way that we can't find IB, we cannot determine the gain either, because we don't know what gain is it. So the third method, let's say like the third necessity tool is, if you can't find IB and if you can't find the gain in either way, then what you need to do is to assume that IE is the same, it's approximately equal to IC, and then use those values. Anyway, so that was this exercise, and I'll see you in the next one.